everyone, I'm Duho Chung, a PhD student from Yonsei University, Republic of Korea. Today, I'm excited to present a work titled Real-Time 3D Perception System of Construction Equipment for Autonomous Mobile Robots. Here is a brief overview of today's presentation. As many of you know, automation using mobile robots is gaining a lot of attention in construction industry, especially to improve both productivity and safety. In recent years, robots have been tested for various tasks such as 3D reconstruction, material assembly, construction automation, or safety monitoring. However, construction sites are very different from structured environments like factories. They are highly standardized and constantly changing, which means that new materials being placed, workers moving around, heavy equipment operating at unpredictable times. These kinds of lack of standardization and the presence of dynamic obstacles makes it extremely hard for robots to operate autonomously. In other words, autonomous robots must do more than just avoiding obstacles. They need to understand what's around them, how things move, and how that affects their task. That's why real-time 3D perception of construction equipment is such a critical step towards true on-site autonomy. On active construction sites, mobile robots operate alongside heavy equipment and each machine moves differently, which means that it's not enough to just avoid moving objects. If the robot doesn't know what the object is, then it can't predict how it might behave. For example, a stationary excavator can just still swing its arm unexpectedly. If the robot fails to recognize these kinds of machines in real time, it can accidentally enter their work zones, causing collision risk or forcing frequent replanning of its own path. That's why robots must detect both the position and the type of these kinds of equipments. So, we propose a real-time 3D perception system that detects and localizes construction equipment using a single mobile LiDAR sensor. So why do we use mobile LiDAR? Unlike fixed or vision-based sensors, mobile LiDAR can capture high-density 3D data in real time over a wide area, offering significant on-site advantages. And because of these advantages, it becomes a powerful tool for 3D reconstruction and structural quality control, as you can see in this image. In other words, with just one sensor, we can monitor both the built environment by 3D reconstruction and the dynamic workflow by tracking the movement of these kinds of equipments. So our work has the potential of forming a truly comprehensive progress monitoring system for construction sites. So here's an overview of our proposed system. So the raw point cloud data collected by the robot is processed by two main modules in parallel. A 3D detection model that identifies the type and position of equipment in each frame, and a SLAM algorithm that estimates robot odometry and builds a global site map. By combining these two outputs, we can convert the detected bounding boxes into a global coordinate system, allowing the robot to continuously understand where each machine is and how it moves over time. This is the hardware setup we use for both data collection and real-time processing. We deploy the Quadruped robot, the Unitree Alien Go, to navigate active construction sites. Mounted on top of the robot, there are three key components: a Velodyne VLP32 mobile LiDAR, a microstrain IMU, and an Intel NUC 11 mini PC equipped with the NVIDIA RTX 2060 GPU for onboard detection and mapping. To detect construction equipment in real time, we used VoxelNest, a voxel-based 3D object detector optimized for lightweight real-time applications. VoxelNest starts by converting raw point clouds into sparse voxel features and process them through the fully sparse convolutional backbone, ensuring computations happen only where data exists. For prediction, it compresses the voxel height to create a bird's-eye-view feature map, which then it is refined using lightweight 2D sparse layers, which means that by minimizing unnecessary computations and avoiding dense feature maps throughout the pipeline, VoxelNest achieves fast and efficient inference suitable for mobile platforms. To localize the detected equipment consistently, we integrated VoxelNest with a SLAM algorithm called LeoSAM. LeoSAM uses LiDAR and IMU to generate precise robot odometry. Using this odometry, the 3D bounding boxes detected by VoxelNest are transformed into a global coordinate frame. On the left, you can see the initial detection results in the raw point cloud frame. In the middle, those results are integrated into the SLAM map and align with the robot's estimated position. And finally, on the right, we show how these detections are recorded and accumulated on the global map over time. This enables long-term tracking of construction equipment and supports higher-level analysis of site workflows. For the experiments, we remotely operated the Quadruped robot at 4 different construction sites to collect point cloud data. We focused on 4 types of construction equipment: excavators, dump trucks, graders, and rollers. Among the 4 sites, 3 were used for training and validation, and 1 was reserved exclusively for testing. As we can see in the table, we constructed a dataset with 1,246 frames for training and validation and 261 frames for testing. To compensate for the limited amount of construction-specific data, we applied transfer learning starting from pre-trained weights in the KITTI dataset. To optimize the model for construction environments, we applied transfer learning using pre-trained weights from the KITTI dataset. Then, evaluated 4 fine-tuning strategies, each reaching different portions of the voxel backbone. In the first configuration, we performed full fine-tuning, training all layers from the pre-trained model. In the second setup, we froze the first 2 sparse convolution layers and trained the rest. And in the third case, we froze the first 4 backbone layers. And finally, we froze all 6 convolution backbone layers, training only the detection head. As shown in the table, the best results were achieved by full fine-tuning, especially for equipment like excavators that are structurally different from vehicles in urban datasets. And I think this clearly demonstrates the domain gap between autonomous driving datasets like KITTI and construction-specific environments. And our final configuration achieved the average precision of 74.5%, showing a reliable detection performance. And beyond accuracy, we verified the system's performance in real time by deploying it on our ROS-based setup. The whole system maintained an inference speed of 2.8 Hz on the robot, making it practical for real-world robotic development. Here are some visual examples of the real-time detection outputs at the construction site where the test dataset was collected. And as you can see, the system successfully identifies multiple types of construction equipment as like excavators, dump trucks, graders, and rollers. So, well, for the strengths of our research, our system enables real-time 3D detection and global localization of multiple types of construction equipment using only a single mobile LiDAR. And by continuously recording the positions through stand-based mapping, the robot builds a consistent global map and achieves long-term perception of equipment movements and working areas. So these capabilities support several practical applications on construction sites, like maintaining safe distance from heavy equipment, enabling adaptive task planning for autonomous robots, and ultimately supporting comprehensive progress monitoring by combining the classic structural quality control with an equipment-based progress tracking with just one sensor. This makes our system a strong foundation for automated and scalable site management in dynamic construction environments. Now, let's briefly discuss the limitations of our current work and future research directions. Compared to autonomous driving datasets like KITTI, which contains over 7,000 frames from diverse urban environments, our dataset includes only 1,500 frames collected from 4 construction sites, with limited variation in equipment types and scene complexity. Well, since data from the same site is pretty much similar. So the lack of diversity limits the model's ability to generalize to unseen equipment environments, because the model tends to overfit to these specific structures and patterns seen during training. To address this, we are currently exploring 2 main directions. First, we are applying architecture-level improvements to make the model more robust, even under data-limited conditions. And second, we are developing a pipeline to automatically generate synthetic construction site point cloud datasets tailored to autonomous robot navigation tasks. And well, both directions are actively in progress, and the results will be presented in our follow-up publication. To wrap up, we proposed a real-time 3D perception system for construction equipment using just one mobile LiDAR sensor. By integrating a voxel-based detection model with the SLAM algorithm, the system can not only detect equipment in real time, but also map their positions globally. In our experiments, the system achieved strong detection performance across 4 equipment types, even in complex dynamic site environments. We also verified that the system works in real time, showing that it is feasible for real deployment on mobile robots. Looking ahead, this system offers a solid foundation for autonomous construction robotics, enabling safe navigation, smarter task planning, and a comprehensive progress monitoring, all with a single sensor. These are the references used for this presentation. And this is the acknowledgement for this research. And that concludes my presentation, and thank you for your attention, and I'll now be happy to answer any questions that you might have.